This week, the 4 videos that I'm going to present focus each individually on a different common functional. And the idea is to give you some sense of the different philosophies and the impacts that they have and their current utility. I put some equations in and I give you the references in every one of them to each of the functionals, but I'm not so concerned about the math here. Do you want to dig in? That's great. You know, I like to talk about that. But in the end, it's to give you a sense of why they're different. So in each case, I'm going to start with a philosophy. That is the guiding principles that people used in order to put together the functional. And first one we're looking at is B3LYP. And when it comes down to it, the progenitor of this is a guy named Axel Becca. He's a Canadian. He's recently retired, but he has dominated at least one side of the density functional theory thinking for a very long time, and to our benefit. He's been amazing. So his philosophy was this: I want to get the long-range energy density right. That is, I want it to go as 1 over R, because the electron sitting out here sees a +1 potential at large distances. He's going to fit to experimental data. So he says, look, there's some things I want to get right, and I'm going to fit. And as he goes on, he'll use increasing amounts of experimental data. But at some point, he develops a GGA, and that's Becca 88. But he decides that there's no way to get proper behavior for some of the properties he's interested in without exact exchange. So he's going to add that as well. So B3LYP is a hybrid generalized gradient approximation. So hybrid means that it contains some exact exchange. That is, you use the cone-sham orbitals and you calculate the exchange integrals just as you would in Hartree-Fock. You can get a portion of that based on arguments from the adiabatic connection theorem. The GGA, so it's got gradient information for X and C, exchange and correlation. It's not just purely dependent on the density, but the energy contributions depend on the gradient as well. So here's the beginning. Here's the first paper. And interestingly, although this is the most used functional in chemistry, or at least it has been, this appeared in the Physical Review. So this is a physics paper. The title is Density Functional Exchange Energy Approximation with Correct Asymptotic Behavior. And this functional right here is referred to as Becca 88. So here it is. What you see is it's the local density approximation with a correction term. And the correction term depends, well, there's local density for LDA as well, but this modifies its contribution. X here is just a reduced gradient. So it is the gradient divided by rho to the 4/3. And a term down the bottom that also depends on the gradient. So it's going to depend on distance because the reduced gradient depends on distance. And it's going to correct the LDA term. Its aims are simplicity. So, you know, I mean, like anything that has an inverse hyperbolic sign in it never feels very simple to me, but it has natural behavior that works. It's got the correct asymptotic energy density, and what he wanted was to get the exchange energy right for noble gas atoms, and what he wanted to do is compare with exact Hartree-Fock, which does pretty well for that. So he fit his parameter, beta, in order to get that right. And this was a definite improvement. But what he found was when he wanted to do thermochemistry, so atomization energies or bond strengths, that it wasn't good enough. And that what he needed was some exact exchange. That is, everything in Becca 88 is still what we call semi-local, depends on position, the density and the gradient of density, but has no concept of what's going on at large distances. Whereas exact exchange, by its very nature, because it's an integral over all space of your orbital, builds in non-local information. So he said, okay, that's the next thing we're going to do. And he did what's a 3-parameter fit of the local density approximation, B88, so it was original GGA, and the exact exchange. And he used somebody else's correlation functional, this Perdue and Wang. Uh, and what he found was BEC88 improved binding atoms, but gave poor ionization potentials. And what he found was he needed GGA for correlation to get the IPs. And then the question is, what will exact exchange do? So here's what the function looks like. It's got local spin density. It's got the difference, certain amount of exact exchange compared to local spin density. It's got his GGA, and then it's got the GGA for correlation. And here's what he did. He just fit it to atomization energies, ionization potentials, proton affinity to atomic energy. So you can see there's more experimental data coming in there. And here are his fits. Now, when you do comparison to the trial data sets that you didn't fit to, you find out it does a little worse than the G2 method, but the G2 method is a wave function based method and is much slower. Doesn't scale nearly as well, and this is pretty comparable. So you say, my gosh, that's an advantage. I can do this calculation faster and get about the same results. So how do we get to B3LYP from B3 Purdue Wang 91? Well, it turns out Becca is not responsible for this, although he's responsible for the B3 part. Li Yang and Parr had built a correlation model not based on a uniform electron gas. I'm sorry, this is ideal gas. It should be a uniform electron gas. Rather, they built it for a model for correlation in helium. That's, classic two-electron problem. That's one where you might think you'd get correlation right for atoms and molecules. And so in this paper in 1994, right here, you see there's no Becca in here, but this person is actually the head of Gaussian, Mike Frisch. And they continued to explore density functional theory, and they decided that they were going to do the following. They were going to get rid of Purdue Wang 91. They were instead going to put Li Yang Parr in there. Li Yang Parr does not naturally go over to local density approximation, but they just put fractions of local density approximation for correlation in there. And he used exactly the same parameters that Beck had for Purdue Beck B3PW91. So in other words, they didn't refit this. They just said, well, we're going to use a different correlation functional. And that when I read that shocks me. It's like, well, why would you think that works? But it turns out it's pretty darn accurate. That, coupled with its availability in Gaussian, at this point, made this method explode. So there are all sorts of tests of it. And I know this is like reading microfiche, but I'm going to show you the next one. Here's a paper you could look up if you wanted. But here's what it says. They test B3LYP with a series of basis sets. They're going to look at heat formation and isomerization energies. They put in an empirical dispersion correction. We'll come back to that at another point. But they look at 622 compounds and the mean absolute errors. So that means you're not going to let a minus error cancel a plus error. You're going to add them all up. In the heats of formation are on the order of 3 kilocalories per mole. They look at isomerizations, and they find that the mean absolute errors on the order of 2 kcals per mole. Remember that bond strengths are 100 kcals per mole. So you're making errors on the order of 3 or 4% of bond strengths, which is quite remarkable. And to a large extent explains why chemists use B3LYP all the time. It's tested, it's dependable. It's not the final word, however. There are more accurate functionals, and we're going to look at that soon.